put me in there because blue is my color. So I'm gonna look good on camera today. Um, the last time I talked to you guys, when we were talking about inverse functions. If you remember, we talked about how, yes, David? Thank you for telling me that. So weird. Why? What is it sharing? It's sharing my email? That's so weird. Let's stop sharing that screen and start sharing this screen. Oh, you know what it is? I got another screen put on, and I just forgot which screen it was. Like I shared the new screen. All I see is information on classified staff. I have no idea what you're talking about there, Valerie. Oh, classified staff are like the office staff. It depends on what kind of accreditation you have. Like everyone's got some kind of like teachers are credentialed staff, counselors are credentialed staff, and like all of our office people or any other, basically anything is classified staff. So you're either credentialed, classified, or administrative. So like I would be credentialed. That's what that means. But way to be reading my emails. So so the last time I saw you guys, when we were talking about functions. Do you remember how I said, like, when we have an inverse function, the domain becomes the range and the range becomes the domain of your inverse. Like your x's and your y's swap, right? And that's what makes an inverse function, right? It's just you swapped all your points where your x's and y's are, you just swap them, and that's your inverse function. So when you are looking at the graph of an inverse function, for every point you have on the regular function, so if I looked at, say, this function right here, right? This graph, like you could see it. You don't need me to try and draw a straight line over it or a curved line over it. But when you're looking at that graph, what it's saying is that like every time I have some point that's AB, the inverse would have to have that same point flipped, right? So if this was like, say, 2, 3, it would also have a point, the inverse would have to have a point 3, 2. Does that make some sense? For every single point that lies on the original function, it would have to have an opposing point, a flipped point. Yeah, like an evil twin, like a mirror image too, right? It just flips over something. So that's all you really need to know. Like I'm not pushing you too hard in trying to verify the functions graphically, other than so that you can kind of look at them and tell, if that makes sense. Like if they're showing you the graph of one, if the opposing graph, the inverse graph or the supposed inverse graph has all the same points flipped, then it's an inverse of that graph, right? And that's all we're really going to go over kind of with the graphically wise, except for one thing. So here they're basically telling you, like, okay, if you have the graph of f of x equals 2x minus 3 and the graph of g of x equals 1/2, as long as all of their points, if I have a -1, -5, I have to have a -5, -1 on the inverse graph. And that's all you really have to pay attention to with that. I haven't given you any problems that are going to take it deeper than that in terms of the graph stuff, which is why I'm not spending too much time on it, because it's more conceptually something that I want you to know than need you to be able to point out, is that they are just inverses of each other. But the other thing that I want to talk about, I think I'm going to have to bring up a new uh, the other form that I had, is that I'm not even going to bring up a page for it. I'm just going to write it out. Is that if I have, remember when we were talking in the beginning about functions and that functions passed what we called a vertical line test, so that when we graphed, whoops, man, I cannot write straight today on this thing. That's really bad, but it's okay. You'll get the idea. So say I have a function that's graphed out, right? This is my very crooked y-axis, and this is my pretty straight x-axis. So, and say I have like something graphed in here, right? And we know it's a function if it passes a vertical line test. If I can drop a vertical line anywhere in it and it only crosses at one point, we know that it's a function, right? Well, the way we can tell if a function has an inverse is if we graph the function and it passes a horizontal line test. So what I'm saying is, say I have graphed the function, I don't know, like some parabola, right? Something like this, right? Perfectly good function. Anywhere I drop a vertical line in there, right? It's only going to cross in one spot on the graph of that parabola, that equation. If it has an inverse, it has to pass what we call a horizontal line test, which means that I have to be able to put a line through it and horizontally, and it will only cross at one point. Now, this clearly does not pass, right? But this does, right? If I go horizontally on this one, it would only cross it once. If I had, say, a cube, if I was graphing, I'm going to do a different color so you could see it. Say I was graphing a cube of something, right? And it'd be prettier than that if it was real, if I knew how to write. But anywhere I went, if I dropped a line horizontally anywhere on there, on this graph of a cube, very poorly drawn, it's only going to cross at one point. So I know that that function graphically would have an inverse. So beyond that, that's all you really need to understand graphically to get through the assignment, because really it's more of a conceptual thing, right? One is that the first part is that for every point I have graphed on a function, it's, if it's an inverse, it has to have the flipped point, right? My x, y's have to change, and that point has to be a valid point on the graph of the other function, the inverse of the function. And the other is, if a function is going to have an inverse, it has to be able to pass a horizontal line test. Same thing as a vertical line test, only now the line is horizontal. It can only cross at one point horizontally. You're only going to have like one or two problems at all even related to this, and they're very, I made sure to keep them as simplistic as possible, because it's really more of a concept thing, right? There's not a whole lot of work that we can do. There was a ton of things that I could give you, like where it was like giving you functions, and then you'd have to figure out which was the graph of that inverse, or if it had an inverse, which one of these graphs was the inverse. And I'm like, that's too much. Like, we don't need all of that. Because more so what we want to work on is finding the inverse of functions algebraically and how we go about doing that. And that's where we're going to spend the rest of our time this period, is using algebra, because everybody loves their algebra, to find the inverse of functions. And there's a very specific set of steps involved with that. And kind of took a snapshot of them that I was going to bring in for you because I think it's a little easier than having me write them all out. Because my handwriting is terrible on this thing lately. And now that I added another screen, apparently I need to go through and set this thing again because it wants to only let me use half of the thing. I'm looking for not graphs of inverse. We're looking for something involving inverse functions though. So if you see anything, stop me. Because it was a photo that I saved and it would make my life so much easier if of course I can't find it, right? Maybe documents? No. Downloads? No. Oh, maybe it's up here. No. I apologize for being so slow with this today. Graphs of inverse functions. Finding inverse functions graphically. It's a little clip like this, but it's not. Is it graphically? Let me see. Let's see if maybe I just wrote it wrong. Yeah. No. Here we go. I just wrote it as graphically instead of algebraically. And so you're going to use the horizontal line test to see if it even has an inverse function, but you probably aren't going to do that. You're probably just going to start with step 2. Hey, Mr. Green. And when we're trying to do this algebraically, we're going to follow this protocol, right? Basically, what the protocol is that we are going to replace f of x with y, and then we're going to switch our x and y, and we're going to solve for y, and that's going to give us our inverse function. And so we're going to start with say I have. We won't even say I have. We'll just have. If I have, for example, f of x equals x squared plus 1. To find the inverse of that function, I'm looking at this and I already know that visitor was Mr. Green. You remember Mr. Green, right? Like the best principal of all time, forever and ever. He was a principal up until last year, and now he works at the district office. He was dropping off guitars for Mr. Gormson. Mr. Gormson and I share a room. It's me and Mr. Gormson and Ms. Walters. It's like the best room ever. I look at this equation that we have here, and I can tell just by looking at it that it's not going to have an inverse, but we're going to follow the steps just to see what happens when we try and solve a function that doesn't have an inverse. Now, if I graphed this, we could tell, because if I graphed it, I know that this is going to graph as a parabola, and it's going to be something like this up here, which means that if I passed a horizontal line through it, it wouldn't work, right? But we're going to go through the process anyways, as if we hadn't done the horizontal line test to see if it would work, okay? And so the first step is we're going to take our f of x and we're going to replace it with y. We're going to go y equals x squared plus 1. And then what it says is we're going to interchange the roles of x and y and solve for y. All that means is where there is a y, I'm going to write x, and where there is an x, I'm going to write y, right? And then I'm going to solve the whole thing for y, which means y has to be isolated. So to do that, I'm just going to subtract 1 from both sides. And I'm going to rewrite this as y squared equals x minus 1, right? Because over here on this side, I have x minus 1, but there's nothing that says I can't write it on the other side. Now, this is y squared. And if I take the square root of both sides so I can figure out what y is, I am going to be left with y equals plus or minus the square root of x minus 1. And if you remember, if it's a function, I can't have two solutions. I can only have one. Every x can only give me one y value. Do you remember that? So this is how I know that this isn't going to work, right? Now, if I'd have just done the horizontal line test like I did in the beginning, you could see that it wasn't going to work because I dropped a horizontal line through it and it crossed in two places. So I could tell you that it wasn't going to have an inverse by looking at it. But who wants to graph every single problem first? Sometimes you're just going to do them, right? But I just wanted to show you what it would look like when it doesn't work. And now we're going to do some problems where it actually does work because, well, let's face it, those problems are better, right? But you can tell when it's not going to work because we got two y values. If it had worked, we would have replaced this y with f inverse of x. Pretend that's a 1. You know, the minus 1 up there that makes it inverse. And then we would just put in those value that value. But we can't do it because clearly it doesn't work. But we are going to work on one that does work and find the inverse of that problem. Oops, I don't want to do that. I want to move this a little bit. I guess I can't move it. I guess I'll just have to move this and tell you what the rules are as we go. So given our next problem, we're going to try and find the inverse of f of x equals the square root of 2x minus 3. So not a pretty problem, but I also know it will work because I know that the graph of a square root usually graphs something like this. And so I know it's going to pass that horizontal line test just by knowing a few things about graphs, right? And what like I know it's how it's going to kind of look. So that means the inverse of that graph would kind of go something like that. So I know it's going to have an inverse and I know that it's going to work. So we are going to follow the rules now. We are going to switch our f of x with a y. We're just going to call this y equals the square root of 2x minus 3. And then we interchange our x and our y. So we will rewrite this now as x equals the square root of 2y minus 3. And we are going to solve this whole thing for y. And the way we're going to go about doing that is if we want to get rid of a square root, because we got to get that y all by itself. If I want to get rid of a square root, I could just square it, but I have to square everything. So I'm going to square this, and I'm going to square this. And I'm going to get x squared equals, and this is just going to be 2y minus 3, because when you square what's under a square root, you just get, when you square a square root, you just get what's left underneath it. And so now it gets a little bit easier to start isolating, right? And we're going to solve it for y. So I'm going to go ahead and I'm going to add 3 to both sides. And I get x squared plus 3 equals 2y. And I'm going to have to divide that 2 out from everything. And so I'm just going to rewrite it as y equals because I'm weird about that. And I'm going to get x squared plus 3 over 2. That is sufficient. I don't need to break that down or find anything else out. I know that I have gotten this right now. And now all I have to do once I've done that is I have to rewrite it as f inverse of x equals x squared plus 3 over 2. There will be times when you have to have like a range and a domain, right? Like say I had a variable in the denominator, I'd have to determine what makes that 0, right? But we've done a lot with domain and range. And if it asks for your domain, it's, well, what can x be, right? And if it asks for your range, what can y be? And sometimes there's going to be parameters on that, right? Like if we look at this, on the original one, like our f of x, like if we look at our f of x and it asks us what the domain of f of x is, we could say, okay, well, that can't be less than 0. So it's going to be anything that makes that less than 0, right? So we'd figure out what makes it 0. So we go, okay, 2x minus 3 equals 0. And whatever makes that 0 would be our starting point of what our domain can be. So, we'd add 3 to both sides, and we'd have 2x equals 3, and then we'd divide by 2, and we get x equals 3 halves. And so 3 halves is what makes this piece right here 0, right? That's a really big circle. I didn't mean to make it that big, right? 3 halves is what makes that 0. So when we're talking about the domain, our domain will start at 3 halves, right? It can't go lower than that because anything lower than that makes that negative, right? And we can't have a negative domain. So it's just going to be 3 halves to infinity. Does that make some sense to you? So that means that the inverse, the range, would be 3 halves to infinity, right? Because we'd just be switching what our x and our y can be. So when we look at the domain of our original function, that's the same thing. This would be the range of our inverse function, right? And the range of whatever this can be, which is like literally any positive number, well, like it could be a lot of things, right? There's a whole lot of things that our x values could be, but I guess they all have to be greater than 0. So our range in this case would be 0 to infinity on the original function. And so that would flip for the inverse. Does that make some sense? Just need a head nod or a no, I'm not getting it. Like I need some. All right, cool, thanks. Do you want to look at another one before I let you guys go, or? Because I got another one for you if you want, but it's kind of icky. It's kind of an icky problem, man. I was hoping to find like a nicer checkpoint type problem to work from, but this one's like a cube root. We could do it though. Let's do one quick one. Do I even have time? Do I have time to do it? What time is it? 101. We have till 112. We could definitely get in another one. For those of you who don't want to, sorry. I'm pushing the limits of what we're getting done today. If I have f of x equals the cube root of 10 plus x. right away, I know that, I don't know. I don't know what this is. I haven't done this problem yet, so I'm like as good as you with this one. But we're just going to assume that it has an inverse, and we are going to switch our y, our f of x with y, and see what comes up, right? But it should be fine because cube roots don't usually have multiple solutions. When I want to take it out of this cube, well, first I need to switch my x and y values, right? So this is going to be x equals the cube root of 10 minus y, right? And then when I want to go to solve this one, all I have to do is raise everything to the third power, right? So if I raise this x to the third power and I raise this to the third power, I'm going to be left with x cubed equals 10 minus y. Because just like with the square root, if I raise it to the third power, all it's going to leave me with is that bit underneath, right? And so when I go to solve this for y, I'm going to start by subtracting 10 from both sides, and I get x cubed minus 10 equals negative y. And I don't care what negative y is, I care what y is. So I'm just going to divide everything here by negative 1. And it just changes the signs of everything. So we're going to call this y equals negative x cubed plus 10. And that is my inverse. And all we have to do now is write that as an inverse of x equals minus x cubed plus 10. So not too bad, right? So switch your f of x with a y. Swap your x and y and solve for y. And then use that y and write it as the inverse function. Yes. You change the sign of x and y values when changing them. No. No, yes. I left this, so like the sign here, I had this minus y, and so I divided everything by negative so that I'd get a positive y. But it changes the sign of everything because I divided by negative 1, or I could have multiplied by negative 1, it would have had the same effect. Does that make some sense? Like, are you talking about this step, like right in here, where, well, you want to get like a positive y equals when you're done. So whatever you have to do to figure out what y equals and not like negative y, 10 plus x to 10. Oh, no, I just wrote the problem wrong. This should have been plus all the way through. So pretend we started with a negative in the beginning. Yeah, that was that was a very good catch. I didn't even see that. We started with a positive and I acted as though we started with a negative. That was just an error on my end. So, yeah, that problem was actually even easier than I made it because if we'd have done it with a positive all the way through, we wouldn't have had to do the whole dividing by 1, right? Because it would have already been positive. But I feel like it's easier just to change it to a negative and then pretend I was right instead of doing a whole nother problem. So I'll see about getting some other practice problems and maybe making a little video and posting some video of other problems in there for you guys. Or just going on YouTube and gathering a couple and posting them on your Google Classroom. But that's really all there is, which is good because we're almost out of time. But if you guys have any questions or you need some help with anything, I will be in hoist support at like 2:05ish. Okay. And otherwise, go forth, be awesome. Remember that Thursday is just going to be a tutoring day. Come in, check in for attendance. But if you don't have any questions, you'll be free to go. All right. Have a good one. Peace.